I'm Dan Helmick, and I'm presenting with Louise Chamberlain on enabling large block sizes to facilitate adoption of large capacity QLC SSDs. Overall, we'll give you the punchline right up front. Samsung's Ghost team has been leading the enablement of large block sizes in Linux. Luis is a representative here today, a lead on that effort. And there's been an evaluation of what are the potential OS changes, focusing on Linux in particular, to facilitate large capacity drives, QLC in particular, since they are some of the largest capacity drives. And that inherently means that we have a large indirection unit that's often coming with those large capacity drives. So quantifying those software impacts and then propagating those changes through all the layers. And the end conclusion that we're going to walk you through the story as we present, but we conclude that increasing the LBA sector size isn't really the best for the overall ecosystem. That was what we concluded. We'll present some of that reasoning. And we're actually recommending some new requirements on atomic power fail, specifically AWUPF, being larger than the indirection unit. So we'll walk through that as we present. What is an indirection unit, an IU? It is a grouping of data that an SSD tracks the data. So today, an industry norm is that we have a 4 kilobyte indirection unit. And this is independent of whether we have a 512 byte sector size or a 4K sector size. We're expecting larger and larger IU sizes. We're seeing that in the environment today. And really a focus problem that shows up with our customer base is if they do a write to a smaller unit than the indirection size, for example, 512 bytes to an indirection unit of 4K, you'll see a read, modify, write penalty on your performance. So it's very noticeable already, and with larger IUs, it becomes more and more noticeable. Already out there, we have optimal host behavior for large IUs. We do have a way to avoid read, modify, writes already. OCP data center NVMe specification has already solved this with a requirement to report the IU size in NPWG. So there is a way to query and get the IU size, which is great benefit. With this information, hosts today can already move up to the IU size for much of their data. The problem is that not all interactions can go up to that. For example, data that might require strong consistency can't necessarily be moving up to the IU size. They need to make sure that all of their metadata consistently and coherently reaches the media, and that includes on power fail. When we looked at LBA sector format and the potentials of increasing that, the layout is laid here. We see reasons for, right? There's a precedent of 4 kilobyte IUs matching the sector size. There are potential system overhead reductions, kind of overheads of transfers, potential ECC advantages and things like that. The reality is they're either minor or already able to happen. So the 4 is not extremely strong. When we look at it against, we see things like the 512 byte sectors are still around, even though there's been a long transition time, and I don't see them disappearing anytime soon. Because IU sizes may need to increase with every increase in capacity of the SSD, we have this challenging, what are we going to do for a sector size? We're not going to align on 1 if we continue to have increasing IU sizes. We could potentially have new PI standards with the very large IUs and very large sector sizes. And even worse, there's been some hard-coded entanglements of memory page sizing in the host to storage sizing on the sector sizes. So those are two things that are hard to separate in the host software ecosystem. And there are some performance risks of degradations if you're reading a large amount of data and you only care about a small amount of it. When we look at atomics, we can see this and build upon this existing NVMe capability. The atomic write unit normal is basically providing clarity up here in the image in the top. And you can see that when there are multiple reads and writes in flight, it clarifies whether you're going to be reading the old existing data or whether you're going to be reading the data that's coming from the in-flight write. So it provides some clarity. I provide a reference there so that you can read the details. The atomic write unit power fail is a parameter that essentially does the same thing, but it adds clarity when there's a risk of a power fail while this data and the commands are in flight. They're essentially doing the same thing, but it's a little bit more restricted. And this power fail consistency is really where we need to add that in order for the host software to move more of their host software stack to the IU size.
So the challenge really then is, the question is, how do you make an operating system write aligned to the IU without moving the LBA format forward? So we looked into that, and it was challenging, but this ends up being that we have a solution in place, and it's a research and development effort that has been existed in the community for over 16 years now. And thanks to a lot of developments in the Linux kernel, this is now a bit easier to do. So essentially what we've done is we have modified the page cache to take advantage of some of the changes that we have now in the Linux kernel, like folios, IO map, to make it easier for you to modify the page cache to align the writes. So essentially, let me be clear here that this is an operating system change to enable you to essentially write every file system write aligned to the IU. So it's a memory management problem, and we solved it, and we've proven that this can be solved at the OS level. So the boxes here that you see in this diagram that are in blue are essentially the modifications that we've made to the Linux kernel. The things in blue and black are the changes that we've made to enable large block sizes in the Linux kernel. As of today, the 6.12 release of the kernel, you can essentially mount a 64K block size file system on a 4K x86 system. That was not possible before. The things in black and white on the lower part of the diagram are things that we're looking forward to making future changes for to enable you to also leverage and support larger sector size. Now, this may be a bit fuzzy to you guys, so I think it helps to try to think about this in a tree diagram form, where on the complete left-hand side of the tree, you basically have what we, non-large IU drives, your standard 4K IU drives with, 4K block size, 4K, atomic. Then you have the lower left part, not the extreme left, but kind of like in the middle. That is essentially what we have for QLC drives today, which is basically large IU drives with an NPWG of 16K, but with a 4K atomic. Now, what we're essentially considering here is for supporting where you have the large atomic to enable you to go to the right-hand side. That essentially enables a large sector size. Now, with LBS today, you don't need a large atomic to leverage LBS. You can use it today on a 4K LBA format drive. In fact, you can do so even on a 512 LBA format drive as well. But obviously, this helps with alignment for QLC. On the right-hand side, that's what we're aiming for. Now, this begs the question, what's the actual advantage of these things? So to try to evaluate that, we need to consider what are the alignment benefits that LBS provides for large IU drives. So you can do this with IO introspection. Now, this is a bit complicated, so I'm going to go over this a bit. We essentially have determined that a large atomic essentially allows you to provide IU alignment determinism. Now, we've implemented a utility called block align, which is an eBPF utility, which allows you to do real-time IO introspection, so that way you can see what the histograms are for IO and also the alignment. What we can also do then is compute the worst case WAF that you would see, assuming that an unaligned write implicates a read modify write. Now, what you will see here is that there's 3 different workloads. One of them is using FIO to write 1 million files, 4K files, using BS equals 512. That essentially is telling FIO, write every 512 from user space. What you will see here then is that there's only one column here that is using 16K sector size, and you have perfect IU alignment. The other workloads are essentially workloads with databases for 12-hour suspense runs with different database page size configurations. And all of this is basically different file system configurations. We even include here on ext4 workload analysis as well, which also shows that LBS provides even improved IU alignment than ext4 with 16K cluster size, which is what the industry is using today for databases. The other thing that comes out here is all the green stuff on the right-hand side. And it begs the question, given that you have such great alignment without the atomic, why do you need it, right? So we know that we can get IU alignment determinism. That's perfect, that's great, but what about the atomic benefits? Well, so we've heard from hyperscalers that there's gains for database performance. But the benefits that we've heard are pretty remarkable to the point that we had to go and verify this. So we've done the analysis. This is basically the result of running sysbench with and without disabling the InnoDB double write buffer on MySQL. This is 12-hour TPS results. And what you see on the top, on the green, is basically the TPS values when you disable the double write buffer. Not only do you get better TPS values, but at the same time, you can also look at the variability, the width of the graph. That's essentially the variability. So we define the TPS variability as the square of the standard deviation. The bottom one, you can see it's a bit thicker. So for Postgres, this is a bit different, right? You have much more variability. But we've also implemented this and supported this into KDevOps, which you could basically use to try to go and, if you want to see for yourself to see if this is actually the same results, you can actually try to reproduce these tests either on bare metal or any cloud provider that you have. So let's try to look at what the variability differences are if we want to try to visualize this a bit clearer. So we essentially see a TPS variability reduction about 3.54. That's huge. And that's essentially what we heard from hyperscalers. So we've confirmed that. For Postgres, it's a bit different, much, much more. And I'm not sure if folks have been talking about this, but these are pretty remarkable results. So, yes, they're extremely valuable. And remember the complete left side of the diagram that I showed where you have existing drives? This was run on existing drives. So you can still get huge benefits just from the large atomics on existing drives as well. Hence the greater than equal recommendation for the IU. This begs a few other questions. OCP v3 racks comes with power supplies with battery backup unit. Well, why don't you just use them and basically forget about the atomic power fail, right? So how long can you sustain without power with a battery backup unit? Analysis shows that this is about 4 minutes. Correct me if I'm wrong, guys. Am I right? Any battery backup unit folks here? That was my analysis last year. I dug a bit into this. Then it's also possible for you to dynamically configure a power supply unit with a battery backup unit only to provide power to specific servers. So with that, you can actually even fake the atomic up to the wound, which is huge. So it begs the question, do you guys trust your battery backup units that much? So I'll let Dan finish on the call to action.
Thanks. So what we've presented here is an enablement so that all host IOs are confidently able to move up to the IU size without losing consistency and coherence. I see this more as a start of a conversation. I think that we want to carry this conversation here today in this presentation, and we want to move it move the conversation into the storage project and bring that to discussion. So if you have an opinion, please bring that as well. For those that are looking at playing with this, it was already described, the tests, we even put some code snippets there. So LBS is available upstream in Linux today. And otherwise, there's a little bit more links for information, and we'll be happy to take any questions.
Great stuff. Let me return the favor and start with a call to action for you guys. And with luck, you've already done it, so it'll be real quick. A lot of what I see here is single IU writes. Please make this work for multi-IU writes. So if I do 128K write and the power fail atomicity is 32K, I get 4 32K atomic writes that don't fate share. They just all have to be atomic. Please do that if you haven't already done it.
Certainly, that does make sense as a request,
and I will plead guilty in that I might be one of your problems. There is a first shot taken at this in the NVMe standards. If we got it wrong and you can't make it work in running code, come tell us and we'll go fix it, because you're now digging in exactly the place that what's called multiple atomicity in NVMe was supposed to solve.
Yep, I agree. I've also recognized the value of tying multiple atomicity into this, yes.
Great work, great presentation. I'd like to ask you to change in your table. You referred to the write amplification factor in the far right column. Find another word. The reason is because if I've got a 4K file system with a 16K IU, like you said, I'm going to write 4K, it's going to read 16K, I'm sorry, 4K with the 4K, yeah, with the 16K IU. Your logical block is 4K and your IU is 16K. So you're going to report that the read modify write is a write amplification, but it's different than write amplification the way we usually think about it. Now, if the application is writing, call it 100 bytes, right? So from the application's point of view, it wrote 100 bytes, but the amount that the drive is going to write is going to be 16K. It doesn't, if the IU is 16K, it doesn't matter. So it's not really the same thing as write amplification. It's a consequence of the block size. It's not, you know, GC or anything like that. It's simply induced by the IU. It's not WAF. So
Yeah.
Please find some other way to refer to that.
Clarifying the read modify write impacts versus the garbage collection write amplification.
Exactly, yeah.
Yeah, you know, actually, it was a bit difficult for us to explain that. That's why we have the worst case workload WAF. And, you know, maybe we should come up with a different term for that, right? Because, you know, where we started seeing some of this stuff, actually, Micron did a good work in doing some of this analysis for 16IU drives last year. So we borrowed that, but we actually wrote an open source implementation that did the IO introspection. But it does beg the question, if you guys have a better idea of what we should call this is one of the struggles that we've had. How do we explain this, right? Because this is theoretical workload WAF. So we can also measure it and compare it, but that's separate work. But I agree that, you know, making it very clear that this is the worst theoretical, you know, workload WAF.
Refer to the granularity somehow. Something like that. That's the closest I can come to. Get the word granularity in there.
It'd be great if we can all agree on a term. That'd be fantastic, you know. So was the recommendation granularity WAF? Is that right?
All I was saying is it's a consequence of the course granularity. So if the word granularity can be replace WAF somehow, or some decoration around granularity, okay?
All right, it looks like that's all the questions. Thank you.